Good morning to all. We are seeing the videos on control systems. The topic what you're going to see now is controllers from Unit 2 titled Time Response Analysis. I am Divya, Assistant Professor in EC Department, R.M.K College of Engineering and Technology. Let's get into the topic now. Before seeing about controllers and its types, I'll tell you where the controller will be placed in a control system. What we are seeing now is a block diagram of automatic control system. Now we can see here error detector where we are getting two inputs. One is our reference input, that is our input signal, other one is the feedback signal. Output of this error detector is called as error signal. This error signal is amplified and it is given to a controller, and the controller produces control action. This control action will be given to the actuator and then to the plant. So here we have a controller. The error detector and amplifier controller are combinedly called as automatic controller. Controllers. It is a device introduced in the system to modify the error signal and to produce a control action. The manner in which the controller produces the control action or control signal is called as the control action. The controller thus modifies the transient response of the system. We have many types of controllers. Let's see the name of one by one. First one is two position, otherwise called as on-off controller. Second one is proportional controller. Third one is integral controller. Proportional controller is shortly called as P controller. Integral controller is shortly called as I controller. Then proportional plus integral controller, in short we call it as PI controller. Fifth one is proportional plus derivative controller, we call it as PD controller. Proportional plus integral plus derivative controller, we call it as PID controller. These are the 6 types of controllers, among which the first one is two position or on-off controller. Here the control signal U of t is equal to U1 when E of t is less than 0. When E of t is more than 0, our value will be equal to U2. That is, we will be having only two positions, either U1 or U2. When we take Laplace transform for that, we will get like this, either on or off. So the error signal U of s is the input given to the controller, and the control signal is represented by the value called U of s. It is either U1 or U2. Second one is proportional controller. Here the control signal U of t is proportional to the error signal U of t. So when we make the proportionality to be equal, we will introduce a constant, proportionality constant, we call it as K suffix P. When we take Laplace for that, we will be getting U of s is equal to Kp into U of s. So transfer function is U of s by U of s, that is equal to Kp. So the input to the controller is U of s, output is control signal U of s, the gain is Kp. The effect of proportional controller. When a proportional controller is introduced in your system, it affects the transient response in the manner that this increases the loop gain of the system, and because of this increased loop gain we achieve the following characteristics. They are steady state tracking accuracy, disturbance signal rejection, relative stability, and the decreases of sensitivity of the system to parameter variations. These are the 4 advantages that we get because of introduction of proportional controller in a system. But the drawback of this type of controller is it produces a constant steady state error. Third one is integral controller, in short I controller. Here U of t is proportional to integral of E of t into dt. So proportionality constant, I am introducing a term called Ki into integral of E of t into dt. When we take Laplace transform for this, we will get U of s is equal to Ki into U of s by s. So transfer function U of s by U of s is equal to Ki by s. So Your input to the controller is E of S, output is control signal U of S. The gain what we are going to achieve is KIS. The effect of integral controller on a system is it removes or reduces steady state error without the need for manual reset. So we call this type of controller is called as automatic reset. Proportional controller introduces a steady state error. This integral controller reduces or removes a steady state error. The drawback of this integral controller is it may lead to oscillatory response of our output. So since we have oscillations, our system may become unstable when we use integral controller alone. The next type of controller is proportional plus integral controller. In short, we call it as PI controller. So here your control signal U of t is proportional to error signal as well as proportional to integral of error signal. So we have to make it equal by introducing proportionality constant case of xp. Then we are going to take Laplace transform. We get U of s is equal to Kp into U of s plus Kp by Ti into U of s by s. So when we take transfer function U of s by U of s, that is equal to Kp into 1 plus 1 by Ti into s. So now we have proportionality, then we have integration. In combination we have Kp into 1 plus 1 by TAS as the controller gain of PI controller. The effect of PI controller on a system is it introduces a 0 in the system and also increases the order by 1. So this reduces the stability of the system. So higher order systems are less stable than compared with lower order systems. So since the order increases by 1, this controller reduces the stability of the system. This increases the type number of a system by 1. This reduces the steady state error. Proportional plus derivative controller, in short PD controller. Here U of t is proportional to A of t plus d by dt of E of t. So we have to make proportionality to be equal. We are adding a term called proportionality constant case of xp. So when taking Laplace transform, we get U of s is equal to Kp into U of s plus Kp into TdS into U of s. So when we take transfer function, we get U of s by U of s is equal to Kp into 1 plus TdS. So we have proportionality, we have derivative. So in combination, we have Kp into 1 plus TdS or TIS. The effect of proportional plus derivative controller is it increases the damping ratio of the system and it also introduces a 0 in the system. So addition of a 0 may increase the peak overshoot and reduce the rise time. This is very much important for our system in terms of time response. But the damping ratio is also increasing, which also reduces the peak overshoot. Last one is proportional plus integral plus derivative controller, that is PID controller. So U of t is proportional to error plus integral of error plus derivative of error. So when we take Laplace, first we have to make proportionality to be equal by introducing a term proportionality constant Kp. Then we are taking Laplace transform. U of s is equal to Kp into U of s plus Kp by Ti into U of s by s plus Kp into TdS into U of s. So transfer function is Kp into 1 plus 1 by TIS plus TdS. Three terms: proportional, integral, derivatives. When we all together, we will be having Kp into 1 plus TIS plus 1 by TIS. Here we have to note down one thing: derivative controller is not used alone in the control system. Why? Because derivative controller takes control action whenever the error signal is changing, rate of change of error signal. When the error is not changing, when the error is constant, a derivative controller will not take any control action. So derivative controllers are never ever used alone. It is combined either with proportional controller or with proportional plus integral controller. I hope now we all have a clear idea about what is meant by controller, what are the types of controller, and what are the effects of those controllers on control system. Thank you all. We'll meet again in our next video.